been countless epidemics and pandemics that struck different parts of the world. The earliest recorded being the Actinian plague that occurred in the years 165 to 180. This plague alone took the lives of around 5 million people. More recently, we have also experienced the harsh effects of both epidemics, such as SARS in 2002 to 2003 and MERS in 2015 until present, and pandemics such as HIV and AIDS, which began in 1981 until present, and Ebola in 2014 to 2016. Before we proceed any further, it is important to note the difference between the terms epidemic and pandemic. Epidemics refer to the rapid spread of an infectious disease to many people. The way pandemics differ from epidemics is basically their severity. Pandemics often cover a wider geographical area, causing infection and, in worst cases, death to more people. Moreover, pandemics are often associated with social disruption, economic loss, and general hardship. In the status quo, we are facing a global pandemic that has taken the lives of approximately 6.2 million people as of May 3, 2022. In the Philippines, the COVID-19 virus has managed to take the lives of 60,458 individuals with 3,688,292 total number of cases since the pandemic began. As of May 16, 2022, there are 2,688 recorded active cases in the country. As shown in the past up until the present, it is undeniable that pandemics are bound to occur for as long as humans live and travel from one place to another. This is why it is essential to represent these epidemics and pandemics in mathematical equations in order to study their behaviors and effectively address them. The first epidemic model was introduced by Piotr Michrovich Enkel. When expressed in modern mathematical notation, his model would look like this. Here, C sub t represents the number of individuals infected in the time interval t. S sub t represents the number of susceptibles in the same time interval, and N sub t denotes the population or the total number of people. K, on the other hand, denotes the number of contacts a susceptible individual has in one time interval. But this model seems a little too complex for us to dissect. Luckily, over time, this model has been revised and edited for easier understanding. The FIR model proposed by Ronald Ross William Hamer in the early 20th century is one of the most basic models in epidemiology that is still utilized today. According to a paper by Christopher Cano, the FIR model comes as a system of 3 non-linear equations, each representing a specific group of people in the situation of an epidemic or pandemic. S of t represents the part of the population that could be infected with the disease, also known as the susceptibles. I of t, on the other hand, denotes the number of individuals who are infected and thus have the ability to infect others. While R of t represents the recovered population who can neither contract the disease nor infect others with it. In the system of differential equations we saw a while ago, ds over dt then represents the change in the number of susceptibles with respect to time, di over dt denotes the change in the number of infected individuals with respect to time, and dr over dt represents the change in the recovered population with respect to time. ds over dt is equal to negative a times s times I for the reason that the more interactions the susceptible population, as represented by s, has with I, or the infected population, the more it is likely for the susceptible population to get infected. We take the product as a negative value because we know that as more people become infected, less people will be considered as susceptible as they move their status to infected. Which leads us to our di over dt. The change in the number of infected with respect to time is equal to the magnitude of the amount of people who transition from being susceptible to being infected, minus bi, which represents the population who have recovered from the disease. So as people are transitioning from being susceptible to being infected, as represented by ASI, people are also leaving the infected population and recovering from the disease, as represented by minus bi. The magnitude of bi, known to be the number of individuals leaving the infected population and recovering from the disease, is then the equivalent value of the differential dr over dt, or the number of recovered individuals with respect to time. So in a town with a population of 500 individuals, we can expect our SIR model to be represented as this graph. We can observe that as time passes by, less individuals are considered susceptible as they are infected with the disease, while more individuals are considered recovered as they recover from the disease. We can also observe that the graph of the infected population first increases but later decreases because we know that in the beginning, a lot of people will be infected. However, as time passes by, more people will recover from the disease while less transition from being susceptible to being infected. Through the SIR model, we are able to understand the behavior of epidemics and pandemics through the interactions of the susceptibles, infected, and recovered. This gives us a glimpse of how mathematics can help us understand these diseases and how we can lessen the transmission of the disease through avoiding interactions between the susceptibles and the infected. Moreover, in the equation ds over dt equals negative ASI, the variable a represents methods of how we can lessen the number of people catching the disease, such as washing our hands, while s, or the number of susceptibles, at the onset of the epidemic or pandemic, can be lessened by vaccinating the population, thus rendering them immune rather than susceptible to the disease. These show us ways on how to manage epidemics and pandemics and prevent them from worsening. Mathematics is truly remarkable in solving problems in the modern world. We learned that through mathematics, we can model epidemics and pandemics and to an extent predict their behaviors, all while finding ways to lessen their transmission. It is through mathematics that we are not only able to solve our problems face to face, but also battle invisible foes such as epidemics and pandemics.